Hi everyone, welcome to MapleSoft's presentation here at Rockwell Automation Fair 2020. Today we're going to talk about optimizing your control strategies for less with virtual commissioning. And at MapleSoft we have a tool called Maplesim will show you how that all works. My name is Chris Hardwar. I'm the Vice President of Business Development.
I'm Chad Schmidtke. I'm the Senior Director for Maplesim Development. I work very closely with Chris and our applications engineering team, and looking forward to talking to you about our solutions today.
Thank you. Let's get started. Today, here's an overview of what we'll be talking about. I'll give a general introduction about MapleSoft and our company. I'll talk about simulation in general and what value it can bring to the OEM, the machine builder, or your company in general. Then we'll talk about Maplesim and Emulate 3D. What really is the difference? You may have heard this through the Rockwell channels already, but I'd like to highlight the difference between the two tools. The simulation workflow and application examples will go deep into some examples and how the workflow actually works. And then we'll end with a summary and wrap up. Company overview. So MapleSoft actually started about 40 years ago, and it was from the research project at the University of Waterloo in Ontario, Canada. It was based heavily in mathematics, and the company ended up being founded in 1988. Today, we're a leading provider of high-performance solutions for engineering, science, and mathematics. And we're in over 8,000 educational institutions, research labs, and companies. Over 250,000 STEM students have used Maple, our mathematics product. And in 2018, we spun off a company focused on education for learning mathematics. We've done our simulation groundwork over the last 10 plus years in aerospace and automotive. We have a global presence. We're part of the Cybernet group. We have offices in Canada, China, US, Germany, UK, and Japan, over 30 partners worldwide, and we have product usage in over 90 countries. Our people are comprised of PhDs, mathematicians, and software developers, and everyone is passionate about math, precision, and technological advancements. We pride ourselves on winning partnerships, and we pride ourselves in our core values, as you can see here. We also pride ourselves in our exclusive partnership with Rockwell Automation. And Rockwell Automation is a leader in digital transformation, and we're going partnered with them to bring you along that journey. We're at every trade show, and we're happy to talk to you either in person back in the past and hopefully in the future, and also here through the Q&A chat session or by contacting us directly. So what does this mean? What does our solution bring to companies? Really, it was born from the cost of design changes, and I think a lot of us are familiar with this. On the bottom here, you see a typical timeline. Usually projects or new product design starts with a concept, system design, and goes all the way to release to market. What often happens, though, is if you find an error or something wrong late in the process, the cost of making those changes can be very high. And we have a technology that provides digital twins to bring those costs down. Because how do those costs come down? Because problems are discovered sooner in the product development life cycle. If they're discovered sooner, the cost of resolving those issues are much lower. So what, other than cost, how else does this help? Simulation in general helps by producing faster development times. Here you have a typical workflow where a concept is on the left, and your concept of your machine or your design goes to the mechanical team. The mechanical team puts it together in a 3D CAD and hands it over to the electrical team. And then the software team takes it to write the control code, and commissioning and deliveries at the end. And there's your customer deadline. And what happens usually, and I think we've all been here as well, is that the customer deadline doesn't move, but often issues are found at the end, and the controls engineers or the commissioning engineers are left in a very stressful situation. what we can do is actually introduce simulation into the workflow, and simulation will be placed right here. So here you would create your digital twin, and now you have a representation of your mechanism or your machine right there on the engineer's desktop. With it being there on the engineer's desktop and being an accurate representation, software control testing can actually start sooner, right, based off the simulation. And then what does that mean? Commissioning and delivery can start sooner, and then you have time saved or a new buffer. Digital engineering with Maplesim. So this is a graphic here that kind of shows the overall workflow for hardware in the loop and software in the loop testing, the connection to Studio 5000. Common applications for the machine builders are if anyone's wanting to find efficiencies for new machines, reduce cycle times, minimize downtime when fixing existing machines, or shorten time to market by improving their machine commissioning, especially when machine dynamics are important. What are some of the features here? Real-time 3D visualization through controls testing. Start your control software testing sooner by testing against a real-time 3D simulation that runs in parallel with Studio 5000, such as Logix Designer. Improve existing machines and cycle times, and then accurate motor sizing for new machines. So what questions can Maplesim help answer? Well, what should the controller gains be? What size motors should be used? How do I improve performance of a machine that is already on site? What is the maximum safe CPM of my machine? Does my control code correctly handle machine failures? How can I test my control code before hooking it up to the actual machine? These are some of the questions that Maplesim can help answer. So I'd like to go into a short video, model-driven innovation, and I'll play that right now.
Companies today are under constant pressure to reduce costs and shorten time to market. At the same time, system complexity is rising due to growing customer expectations and regulatory constraints. To meet these challenges, an increasing number of machine design engineers are making system-level, multi-domain virtual prototyping a key part of their product development process. System-level prototypes save time and money because problems frequently arise from the interactions of subsystems, even when each subsystem meets its own design requirements. Typically, these problems are only uncovered at system integration time, late in the development cycle, making changes time-consuming and costly. By using system-level, multi-domain virtual prototypes, engineers can identify and address these types of design issues long before investing in expensive physical prototypes, and even make improvements to the overall design. Maplesim is the ideal tool for performing system-level modeling, simulation, and analysis of machine designs. It allows you to combine mechanical systems with multi-domain subsystems such as electric drives, hydraulic circuits, electromagnetic components, and heat exchangers. Maplesim allows you to develop virtual prototypes of even the most complex designs easily and rapidly, while providing the power of Maple for design space investigations and parameter optimizations.
Let's go ahead and talk about the spectrum of digital twins and simulation and virtual commissioning. So I'd like to explain some of the differences. Here you have a picture of an assembly line. It has several machines and product is flowing from left to right. But when we talk about simulation, there's a broad scope and there's a detailed scope. On the broad scope, you have tools like Emulate 3D, where really they truly specialize in plant and process level, sequencing and throughput of product, the flow of product from one machine to the next machine. They're really good at doing plant layouts, and they have capabilities for virtual reality and, of course, virtual commissioning. Emulate 3D is a Rockwell product and is very, very good at laying out and doing virtual commissioning for the entire assembly line. That's on the broad scope of simulation. On the detail scope of simulation, we have other tools that focus on the part itself. So here in that picture, you see a part. In this case, it's a suspension component, and when you could see the stresses placed on that part. So very detailed design on the part level. And that's where digital twins on the part level come into play, and tools like ANSYS specialize in those. Where does Maplesim fit, however? Maplesim fits right in the middle. We focus directly on the machine itself. So the prototype of the machine, the motor and mechanism limits can be determined, machine level controller testing, and this is one of the key value areas, is that if you have a machine that requires more than just mechanical, where electrical and hydraulic and other subsystems and different domains need to be connected all in one, Maplesim is there to put it together all in one canvas. And this is based on advanced mathematical modeling. So once again, Maplesim is focused on the machine, whereas tools like Emulate 3D are focused on the entire plant. The digital engineering ecosystem. So this is from Rockwell, the digital engineering. They have identified key value areas, and there are 4 of them. Throughput analysis, optimizing throughput design with simulation of dynamic processes. Virtual commissioning, test, verify, and commission control code before they go into service. Operator training, reduce risk by training workforce in a safe virtual environment. And then machine prototyping, design and validate next generation machines with mathematical models. So Emulate 3D's sweet spot actually is with throughput analysis and virtual commissioning. They're also very good at operator training. Maplesim's sweet spot is with virtual commissioning and machine prototyping. And that's where you'll see more examples further in this presentation. How does Maplesim connect to your world? Let's say if you're a controls engineer or if you're an OEM and you're familiar with Rockwell tools today, it's through the design suites that connects to the Studio 5000 simulation interface. What does that look like? So Maplesim's machine model, which is multi-domain, hydraulics, motors, electrical, mechanical components all together in one simulation, connects to the Rockwell environment via FMI. So basically this is what this is your model gets turned into C code and gets wrapped in an FMI wrapper, which is then called an FMU, which is a standard in the industry. The simulation interface itself takes that FMU and integrates it with Studio 5000. And you'll see more of that a little bit later. So what does that really look like? So your model has inputs and outputs, and the inputs and outputs are then connected to the Rockwell automation world, which is through the simulation interface, and then gets ultimately connected to your ACD file. So output of our model goes to the input of the ACD file, and you can have multiple outputs, and you could also have multiple inputs. In this example, the input here is the product mass. So you can adjust the product mass, and that is actually the input to our model. And you'll see this in detail coming up soon. So I'd like to hand it over now to Chad Schmidtke.
Thanks, Chris. So Chris has given a sort of 10,000 foot view of this process. I'd like to go and look a little bit more granular at it and talk about how you actually go through doing this. So you can start from a concept. Maybe you don't have any CAD yet, and it's just an idea that you'd like to try out. You might have CAD. It might be the 2nd generation of a machine that you're building. You want to try some new pieces on, or it might be a machine that's already in play and there's a problem with it. So either way, the next thing you need to do is put that model into Maplesim, and we can work in all of those scenarios. And once it's there, you can start this sort of rapid feedback loop of making design decision changes and seeing how they affect the performance of your machine before you've had to build anything. So let's take a look at what that might be, or how customers have used that kind of technology to make design decisions before they've built their product. So in this particular case, we were working with a customer who builds mining equipment. Now, to give you a scale of this thing, if you stood beside that tire over there, you wouldn't even come up to the rim. I certainly wouldn't. Maybe you would. You're a bit taller than me. But this mechanism, obviously, if something goes wrong with it, it's out in the middle of nowhere. It's a huge piece of machinery. If something goes wrong, That's a real problem. So they decided, came to us to say, let's take a look. Particularly, we're concerned about sort of this actuation of these giant skips that lift the sort of rock into that bin in the center there. And so looking at, they put together sort of the basics of the hydraulic circuit they had in mind. And they wanted to look in particular at the positioning of those big hydraulic cylinders, as well as where they were receiving their sensor data from, to see if there was any problems in the design as it was going on. They took a look at the stability, and it actually turns out in the initial design there was a problem with the stability set. And I've zoomed in here on a 2D view of the system, but you can see that as that thing is rising, it's sort of vibrating as it goes up. I'm not sure if you're seeing the animation there or not. Okay. The other piece that's going on is that they took different tools inside of Maplesim to run parameter sweeps. So here you can see they're doing comparison on different geometric design parameters of that structure and how it affects the forces that are actually, or the loads acting on that skip. There's a variety of different tools in Maplesim to sort of automate this process. The other thing they looked at, they were running this, and what they wanted to do is make sure that it mapped back to the physical system, but they needed to run it very quickly. So you can see here the frequencies match up with the FEA analysis, but they've also been able to include this mechanism with all the other domains to run the tests like I was talking about previously. A last little thing that they used it for that was interesting was actually the loading on the ground. We had to create for them a ground model. This thing is so massive that it can actually, compress the ground that it's on, and that can affect the working and the lifting of those skips. Now, once that model is built, and I hope I've convinced you that there's real advantage to doing that even before you've built anything. But once that model is built, you can start doing additional things with it. It's not just tweaking the design. You can also do things like sizing your motors, for instance. You've now got a model that has all the proper accelerations. You're not just sort of doing static load calculations, but has all the accelerations and changing inertias to give you an accurate idea of the loads that your motors are going to actually be experiencing. And the other thing you can do, and this is one of the things I want to talk about more about, is the ability to do what we call virtual commissioning. You can take these models that have been built and use tools like simulation interface that Rockwell Automation has recently come out with to attach it to your controller code, so you can actually test your control strategies without, or before you've actually had to hook it up to the real machine. So let's take a look at a customer who used this exact sequence and sort of for a problem that they were trying to solve. Now, their issue was that there was a machine already deployed at a customer site, and this machine, when the customer tried to increase the cycle time to speed it up, it had a problem. It introduced a large vibration when the platen bolts came to a stop and when it was starting up. And this is a lot of mass that you're moving around. And so they came back and they said, hey, we need this faster. This is a difficult thing for them because they either had to go to they were obviously going to have to go to the customer site and shut things down for a period of time to fix the machine. But they had two options. They were going to either have to sort of rip it apart, and one of the ideas they were considering is replacing the single cylinder with two cylinders. They weren't sure if that was going to work, but pretty sure. The other thought was, is there something you can do in the control code and adjust the control parameters in order to make this work better? That's when they contacted Maplesoft and said, hey, can we make a basic model of this that we can maybe do some control parameter testing and control strategy testing on? So the first step was to sort of get the basics of the model together. So, get your inertias correct, get the sizing and the diameters of your pistons correct, the cracking pressures of your relief valves, your check valves, making sure that they've got the right flow characteristics, different things like this that can be pulled from the manufacturer data. And again, this isn't the full hydraulic circuit, but it was a simplified version that contained the critical dynamics for the problem that they were having or exhibiting, sort of a targeted model. Able to create that, and once they had that, they could control and sort of get an idea of how their piece was moving. But then the real step was to match that to what was already in the field. Because of course, if they want confidence when they're updating their control strategies, they want to be sure what they're working on matches what's in the field. They were able to get data from some runs at the customer site, and there's tools in Maplesim for doing parameter sweeps and optimizations that allowed them to very quickly match the parameters that they had in the model, some of the compliances, to the things that, to make it match the results that the machine and the actual plant was giving. Then, once that was finished, they were able to actually see and replicate that vibration that the customer was seeing when they increased that cycle time. Now they had a platform that they could try new control strategies on, that they could tweak parameters on to see if they could reduce those vibrations and allow the customer to speed up the cycle time. So what kind of investment went into this? Was it years of development or, well, no, obviously not. Was the cost of the software that they had to purchase to build that model and to match it, about 2 engineers, 1 week with the total time. Now, it ended up spanning over a little bit more than that as far as the actual time that passed because you had to transfer data back and forth, but the working time was about 2 person weeks of work. And finally, the real benefit was when they went to the customer site, it was down for a minimum amount of time because they'd already tested their control strategy ahead of time. They were confident in it. And so when they were there, they just had to implement it and see the results. And what were the results? They were able to beat, actually, the customer's desired cycle time, so actually able to go even faster. And the beautiful thing was they didn't have to take the machine apart. It was just a change to the control strategy that they were using. And obviously, this was a huge benefit for how they showed the customer their knowledge of the system, but also for themselves, not having to spend all that time with a line down at the customers. So I hope I've given you some motivation for how these kinds of things are being used. What I'd like to do next is show you sort of a brief video of what it looks like when you build something like this hydraulic cylinder or this injection molding machine, what that process looks like in Maplesim. When you open a model in Maplesim, this is what you're presented with. On the left-hand side, you have your different palettes for the different domains, electrical, hydraulic, thermal. You have the central area here, which is where you can actually build your model. And then on the right-hand side is a properties pane that as you select things, it will tell you what the properties are or what's available for that. I'm just going to make that disappear for now to give us a little bit more real estate as we look at this model. I've already set this up in a controller plant setup. So very simplified controller here. And this plant model will be our simple hydraulic single-axis injection molding system. So if I go inside, you can see I've done a bit of a cooking show here. I've already built the hydraulic circuit. However, I would like to show you what it's like dragging and connecting components and working with CAD inside of a model. To that end, let's open up the CAD that we're going to be taking a look at of our hydraulic, our injection molding system here. Zoom out. There we go. We can take a look at it. And really what you usually want to grab from CAD for Maplesim, the inertial properties, some kinematics, and the visualization that you're going to be using sort of alongside while you do your simulations later on. So in this case, one of the important things we have to define, we're going to break this system into 2 parts, this moving platen you can see here, and then the base, which is going to be essentially just the rest of the system. But for now, we've got to define where they're going to connect or how they're going to connect. And in the CAD toolbox, you can do that. If I just select this piece here and say don't show, you can do that just by sort of going in, adding coordinates to it. So you can tell if I put my mouse over top, if it finds some geometric shape, it automatically adds a coordinate to it. Here I'm going to grab this tip point. That's where I'm going to be applying the hydraulic pressure and just add a coordinate to it. Now I can go to the coordinate view and you can see that coordinate's been added. I'm going to call it P, very clever naming system. And because I want it to exist on both of these bodies, because I have to attach them together, I'm also going to go to the reference frame and paste it there. And now this is a reference coordinate, so if I re-import my CAD, that coordinate will appear again. And it will move alongside this coordinate over here. All right, so let's show everything again, show all. This is my system. Don't need to add any more coordinates. And I'm ready to export this. I did add one more coordinate over here in the corner, and this is just a reference frame that sort of says so that when we start the simulation, it's attached to ground. Once I'm done, I can accept. And what that's going to do is create a small library of those two components, that base component and that platen component. And those are what I'm going to sort of drag on here to my Maplesim model and attach up. So here's the platen I'm going to drag in. So that reference, as we said, goes to a ground. I need to attach these 2 points here. Remember, this is that node P that I developed. And I'm going to do that with the multi-body library, just one of the standard joints. So the prismatic joint, I don't know if you were paying attention, but it's to move along the z-axis. So I'll just go over here, select the z-axis. I'm now going to add an additional mass that I had included before. I'll just show this now. And this is just a parameter so that I can modify the mass later on and say, what if there's a tool at the end of this platen? I can vary it for different parameter sweeps, things like that. Finally, I have to attach this. So let's flip vertical, and I'll just attach it to the piston over here. So again, as I said, I've already done the hydraulics. These are just from the hydraulics library. So if I open it up, just drag those pieces on. For these values, for the DC V valve, for instance, I'm just using sort of a stock one. However, if you've got manufacturer specifications, we do have versions that you can set up with a custom lookup table as well. The other thing that's interesting here for the control, and I'm doing this just to simplify this when we export it, is I've got a lookup table here, or I said actually a pair of lookup tables, for the position that I want the platen to move to, as well as the RPM that the motor is going to be required to go through during that motion. So this is a sort of a synchronized table. I can set maximum accelerations and things like that in different types of shapes. But if you want to see what these are doing comparatively or to each other, I'll just stack them and you can see the relationship. I'm including that here again just for simplicity. Once I've got that, you can see at the top level here, I've got a mass piece and then also a conversion factor for that set point for the motor, the pump that's driving the hydraulic circuit, converting that to the rotations for that pump. Now, I'm in Maplesim, I've built my model, and I want to start playing around with it. I want to start investigating how robust it is to certain things. You can do that by running simulations over and over again. So in this case, I'm going to run the simulation. It's going to generate the equations, and it's going to sort of give me plots and a visualization of this system. See, the integration is going to finish very quickly for this system. And I can sort of take a look at the current setup, how well it runs, whether I've got some vibrations, is the position following what I would expect. But another way of doing this is actually to use some of the tools inside of Maplesim directly. So right now I'm going to grab the parameter sweep app. I'm going to load it, and what that does is extract all the parameters from the model and list them. And these are parameters that I can vary to do a sweep, essentially to modify and change over a course of a number of simulations. So the first I'm going to look for is the gain for that controller. I'm going to shift it to be from 0.2 to 2. And I'm going to also add the mass, that mass that we talked about being able to add there. I'm going to include that as well and shift it from 1,000 to 5,000, let's say. Great. And actually, I'll do 10 runs of each of these, so 10 different data points. Once I've done that, I have to say sort of what I want to look at for the model. In this case, I'm just going to grab the probes that I have, and let's look at the pressure PA and the actual position of that end effector, the platen. Once we're done selecting what we want as an output, I've selected time series, but you could select the RMS value or the maximum force, for instance, if that's what you're interested in seeing. I can go off and run this parameter or run the system. What it's doing, it's compiling the code, generating a very fast, efficient procedure that it can run. And here, I'm running 100 simulations, and this is just on a laptop very quickly. And I can start getting my results. So here is, this result sort of shows the envelope of the simulation results. So everything you're seeing goes in between these for the platen position, also for the pressure. You're going to get to see sort of the envelope of those 100 simulations. If you want to go in more detail of this, you can say, well, let's see what happens as we change the mass. So I'm gonna fix this mass and actually just look at sort of the solution sets as I've adjusted the mass. What happens to these solution sets? Hey, can you see they modify a little bit, but likely that gain that's being applied is the bigger piece. Again, you can do this to analyze your system and get an idea of what kind of robustness is there. Once you're happy with all of this, you need to export your model into your PLC programming environment. We do that with the FMU generation tool. Again, we load the system, so it extracts all the inputs and outputs and pieces of the system. The inputs are pretty straightforward for our model. Here's our outputs, those probes that we'd set up. But let's take a look at the export options here. For exporting in the automation context, we often just choose co-simulation. We'll choose the defaults. This communication step size says at what rate the plant model will be expecting to receive information from the controller. And then when we're done, we simply give it a name for the archive and we hit generate. And this goes off and actually creates a compiled version of this model that can be run within our sort of PLC programming environment. Once we're done with this, it's time to switch over to our PLC programming environment and just import or connect to this code that we've just generated to actually do the sort of virtual commissioning and testing of our controller code against the plant model that we've developed for it. So I hope that gives you a feel for what it's like building the model and sort of getting it ready to connect to your automation software. But now let's take a look at, again, what we can do with that model. I mentioned motor sizing before, but what I really want to talk about today is the connection to simulation interface, how you can do virtual commissioning with that digital twin. So I put together sort of a little video that sort of walks through that process, taking that model that was built in the previous step and now hooking it up to some controller code inside of Studio 5000. So we're going to take a look at Studio 5000 simulation interface. The first thing we're going to do is load that FMU that we just generated, or that I generated a little while ago actually, but I've copied over to this machine. And now I'm going to load the ACD file that goes along with it. This is my control file, or my PLC, the file that contains the controller code for my PLC. Once that's there, I verify that the communication paths are set up. Specifically, I want to point that to the 6th slot on my virtual PLC here. And then I want to download the program. So this downloads this module to the PLC that I've got, or the control board that I've got. I should say that this ACD file I've already generated ahead of time, but if you want, you can generate one that's going to automatically take the tags from the FMU and sort of create a shell ACD file that you can add your programming into later. You can do that if you press this information button here and select generate. So now that we've got this set up, we can go about connecting the tags. What's really happening here is that we've got a plant model, that's the FMU, that's going to be running alongside the control program in the ACD file. But they have to be able to communicate back and forth, and they do that via tags. So you can select a tag, drag it across, and say this tag from the FMU attaches to this one in the ACD. Now if you've got a lot of these, it can be quite cumbersome. So there's a nice option here to auto-connect. And when you do that, it'll automatically piece all the tags that you see that have the same name to their counterpart in the ACD file. Now, quick pause. If you'll recall, where did these names come from? Take a look at this subsystem that I generated. Command was the input, plant position, pressure A, pressure B, power, and set point. These are identical to the names that you see appearing here as the tags for the FMU. And these are the names that I then put, to simplify my life, in the ACD file. Once all these things are done, I can go to the Start Simulation tab. Now I'm going to be running this in the operator training mode, so Emulate OTS turned on. I usually turn the acceleration to 10 when I do that. And the last piece that I want to do is launch Maplesim Insight. Now, Insight is a tool that's sort of a companion to Maplesim models. When you export an FMU, you can use Insight to basically do the plotting and visualization for that FMU. So it's not just the code that we're going to be running. We're actually going to be able to see this thing running while we go. I'm just going to hide that panel. You can see I'd run and saved or stored off a previous simulation that I'd been doing. The reason I load a previous is it allows me to bring back up sort of the default views that I had in my simulation. Now that that's ready to go, I've loaded it here, and I can hit start. That's going to actually launch the FMU, start it running, as well as start the ACD program running on the PLC. You can see that's up and running here, and if I look over to Insight, I can see the actual motion of the physical plant being controlled by the controller. Now you can see the controller's got some work to do. There's some choppiness here in the response, but that's okay. The whole purpose here is to be doing this testing, to test the system with the dynamics and test out my controller. So I'm actually going to pause the simulation because I know I've got work to do on my controller. And I'm going to go over to Studio 5000 and go online. Now I'm going to need to upload the model. That's fine. It's going to go off and do that. And once it's done, I'm going to actually be able to edit and modify the control code as the system's running and actually see how the response, or see what the response is. You don't have to do this live, of course. You could be doing this separately while it's running. But let's go back and start that simulation up again. So we're going to continue the simulation. It's going to keep running. And now I'm going to go here, and let's say I've got, maybe my gain is too tight. I'm going to reduce it and see how that affects my system. So now I can come back. You can see that vibration that was happening at the top is greatly reduced. I still have a little bit of wobble here. I've got some work to do on my controller, but it's an improvement from what I had before. And this is the kind of back and forth that you can start doing, playing with your model, once you start using something like Simulation Interface, Maplesim, and its companion app, Maplesim Insight. With these tools, you can start to do virtual commissioning and test your controller code against a plant model with dynamics before you build anything.
Chad, that was great. Thank you so much for giving us an overview of Maplesim and how its connection to Studio 5000 can really bring some true benefit. And for everyone watching, I hope you were able to get familiar with Maplesim for virtual commissioning digital twins and see how it can benefit you in your business. And I hope that you can think about some of these areas. And if you're an innovating company that wants to move forward in new ways, we can help you along that journey as well. If you have existing machines out there that you want to improve the performance on, we can help you on that journey as well. So I just want to say thanks again to Chad, and I have a few slides left that I'll wrap it up with. In summary, the digital engineering ecosystem that includes Maplesim simulations as part of your workflow. In summary, what it really is, it starts with your 3D CAD, the mechanical 3D CAD system that you already have. And then from there, that 3D CAD gets put into Maplesim. The model comes alive with the electric circuit, the hydraulic circuit, the mechanical components. As you saw in Chad's demonstration, it comes alive, and that really becomes your digital twin. And that digital twin gets sent over to Studio 5000, which then allows you to test your control code, to change inputs and outputs, to see what happens, to test in a safe environment, and actually to visualize your machine functioning. And what happens after that, usually typically when you go through this workflow, you have a shorter time to market when developing a new product or a new machine. And the main reasons for this, like I mentioned, prototype design iterations can happen in Maplesim. And then control code testing starts sooner, before the physical build. Or if you do have an existing machine, updates to the control program can be done without being on site. As a Rockwell Encompass partner, we're there for digital twins and virtual commissioning. On the left here, I show a couple of pictures of our kind of our 2019 most popular applications, and that's with packaging machines and with injection molding machines. A digital engineering workflow that includes multi-domain modeling can speed up time to market, allow controlled code creation and testing to start sooner, allow you to play, iterate, and update the machine's design, and innovative features and test scenarios in a safe environment. Ultimately improve OEE of existing machines as well. Advanced mathematical based simulations duplicate real world behaviors. And because of the math engine that's behind Maplesim, you can achieve real-time simulations of the most complex models. And some of the proving ground we've had for this was in automotive and aerospace, where we had to put together complex simulations. And here's a little graph that shows our closest competitor in terms of speed, where Maplesim was able to perform about 10 times faster. In summary, Maplesim is the fastest, easiest way to model machines with motors, hydraulics, electrical, and mechanical components all in one canvas. Models can be connected directly to automation control code environments and then visualized when the control code is being executed. The FMU approach means that Maplesim is not locked to specific hardware. If you have more than Rockwell components, Maplesim can function and work together with those as well. I guess this is probably the most important point on this slide, is we're here to work with you. MapleSoft is here to work with you for pilot projects and engineering workflow assessment. Most of our customers start with us working together with them on a particular design component, on a particular machine, and during the time that we work together, we produce the digital twin and kind of hand it over to the engineers there at the same time training. If you want to know more about virtual commissioning in general, I highly recommend a website called virtualcommissioning.com that Maplesoft is part of. And virtualcommissioning.com, if you follow them on LinkedIn or any other social media, you'll get weekly updates of the latest information and trends happening in virtual commissioning. Actually, Emulate 3D has a great interview on virtualcommissioning.com. Check them out. Thank you very much. The digital engineering workflow is part of Rockwell Automation. We're happy to be part of, and thank you very much for your attention today. Please ask any questions and please provide your feedback in the Q&A. Thank you so much. Bye.